This is IMERMAID Open Call 1 information session focusing on the innovative IMERMAID solutions available to third parties applying under IMERMAID Open Call 1 opportunity. The solutions are grouped into three categories. The first one is looking for chemical pollution monitoring and prevention with 4 available solutions. Moving forward, we have chemical pollution remediation solutions with 4 available solutions as well. And the third one is public acceptance and community engagement, where 1 solution will be presented. At the end, we're going to share more information on the use case methodology used for the development of internal IMERMAID pilots. This methodology should also support you in developing your own use cases described in your applications. Each presented solution will follow the same structure for consistency. First, you will hear an overview of the solutions, followed by technical descriptions, certain applications of the solutions and how those can be used, suggestions for preliminary actions conducted by the third parties, by the beneficiaries, expected outcome at the end of the program, and of course, available technical assistance throughout the duration of the program. First out of the solutions for chemical pollution monitoring and prevention is the electrochemical carbon-based sensors dedicated to organic micropollutants. This solution is going to be presented by Adil Aitiaza from the University of Angers, France.
Thank you, Eli, for the presentation. I will be talking about our solution for chemical pollution monitoring. The solution is about electrochemical carbon-based sensors dedicated to organic micropollutants. So what is our solution? It's an electrochemical carbon-based sensor that can be used for on-site in the real-time monitoring of organic micropollutants in wastewaters. An example of wastewaters is landfill leachate or pharmaceutical effluent. The main function of the sensor is to measure the concentration of selected number of organic micropollutants, for instance, bisphenol A, ketoprofen, ibuprofen, or PFAS. And to measure the concentration of these molecules, we use an electrochemical cell with 3 electrodes. Our work is focused on making the working electrode sensitive to these molecules in order to generate an electrochemical signal. And one of the methods that we use to modify the surface of the working electrode is the molecular imprinted polymer technique. It consists of creating a cavity on the surface of the electrode by polymerization reaction in the presence of a template. At the end, we obtain a cavity that has the shape of the molecule that we want to analyze. An example of the application of the electrochemical sensor is the measurement of the concentration of bisphenol A in a wastewater sample that was taken from a wastewater treatment plant. And by using the sensor either in before or after water treatment process, we can measure reliably the concentration of, for example, of bisphenol A. For example, we used the sensor to analyze bisphenol A in a wastewater sample, and we obtained a concentration in the order of 14 milligram per liter. And the methodology that we usually use for the development of the sensor is comprised of 3 main steps. The first step is to identify the predominant pollutants in the sample, and the second step is to develop the sample. The second step is to develop the sensor, and finally to validate the results obtained by the sample using classical analytical methods. And before implementing the sensor, we suggest that the beneficiary conducts a number of activities. First, it's important to conduct an initial analysis of the effluent by an accredited lab in order to check the presence of the target molecules and the concentration levels of these molecules. Secondly, it's important to assess the need for pre-filtration of the effluent, for instance, the measurement of turbidity. And finally, validate the analytical performance of the sensor in an accredited lab. And by using the sensor, the beneficiary can benefit from a number of advantages. Generally speaking, electrochemical sensors provide or are considered as easy to use technology. They are suitable for on-site water and wastewater analysis. They have minimal sample preparation, and they provide a rapid response. And finally, they have a low cost compared to classical analytical methods. During the implementation of these sensors, we can support the beneficiary or the partner to understand its specific needs and the potential challenges related to the implementation of the sensors. We can offer also trainings, online trainings, demonstrations, and hands-on workshops. We also can provide lessons that we learned from the application of the sensors in other wastewater treatment plants. And finally, the partner can benefit from expertise and technical advisory provided by the consortium and dedicated to chemical pollution monitoring.
A next available solution for chemical pollution monitoring and prevention is the heavy metal sensor, presented by Serena Lasci from the University of Florence.
Thank you very much, Ellie, for your presentation. I am presenting you our heavy metal sensor. What is it? The heavy metal sensor is a miniaturized electrochemical sensor which allows the continuous monitoring of heavy metals in water samples. What does it mean? It means that it is able to measure the concentration of a group of heavy metals, mainly cadmium, copper, and lead, at trace levels. That means microgram per liters or parts per billions. The heart of the system is the sensor, which is a miniaturized electrochemical sensor, which is suitably modified in order to be sensitive against the detection of the heavy metals. This sensor is inserted in a flow system, which is composed by a pump, a potential stat, and a steering system, in which it can be used for repeated measurements of heavy metals by applying suitable electrochemical technique. So finally, the heavy metal sensor consists of a portable system equipped with an electrochemical sensor sensitive to cadmium, lead, and copper that can be detected simultaneously in a complete cycle measurement, which needs more or less 5 minutes to complete the analysis. The results are returned as a current peak that can be correlated to the analyte concentration using a calibration curve or a standard addition method, and then the related calculations. This is an example of water samples, specifically seawater samples, analyzed using the heavy metal sensor. You can see here that it is possible to obtain the 3 signals for the 3 metals if they are contemporarily present in the sample. And this is the corresponding calibration curve that you can obtain for different concentration. Using the calibration curves, you can obtain the concentration from the sample. The heavy metal sensor is applicable to the following sample types: seawater, wastewater, water from treatment plant, influent and effluent. Of course, to be sure that this solution can be applicable to your case, it is necessary to check your samples for the presence of heavy metals, at least at ppb levels. Before to process the sample, it is necessary to apply an appropriate filtration in order to eliminate the solid particles that can create problems to the fluidics. Samples must be stabilized with acidification before the analysis, and a preconditioning step for sensor stabilization is needed before the analysis, but this is just one step that we have to apply when we start the monitoring. Then the sensor is very stable during time. The use of a heavy metal sensor provides simultaneous monitoring of cadmium, lead, and copper with a very high sensitivity level in many typologies of samples. By means the use of a very cost-efficient analysis system coupled with easy-to-use technology and the rapid response time. Due to the reduced dimensions, the system is suitable for on-site use for one-shot measurements, but also it is applicable for on-site monitoring. What we can provide if you decide to use this solution for your case is the expertise for feasibility assessment studies. That means the analysis of the sites and samples that you need to analyze in order to study the best approach for the analysis, a training on the use of electrochemical heavy metal sensor and to perform the electrochemical analysis, the assistance in the development of customized protocols for sample treatments and analysis, and of course, the analytical skills for data interpretation.
Next from the solutions for chemical pollution monitoring and prevention is the PFAS sensors for monitoring water contamination, presented by Vladimir Urushevich from Zentrix Lab.
Hello, good afternoon. PFAS or perfluoroalkyl and polyfluoroalkyl substances are quite a hot topic as a pollution these days, and also known as perpetual or eternal pollutants, because they degrade very slowly or never in nature. They are very widely used class of chemicals in the industry, with the components of common compounds like Teflon and anti-stick coatings in cutlery industry, in clothes industry, in many different branches, and they have increasingly more evident harmful effects on humans and animals, and they are found, unfortunately, as contaminants in water and resulting in soil, air, in biota, and pretty much everywhere. So we offer an innovative electrochemical, meaning relatively standard sensor technology for ubiquitous and on-demand monitoring of PFAS in water bodies, providing rapid response time in measurements with the sampling volumes, and through a low-cost protocol and generally low-cost prototyped initial device. This is the schema of the sensing device connected, of course, to all the relevant hardware. And of course, the connection is directly through the PC or a mobile device through the network, preferred through mobile connectivity. And there is an inbuilt embedded mobile cellular data module with the SIM card communicating and practically doing the acquisition and relaying the readings and measurements to the central backend IMERMAID platform. Otherwise, the electrochemical cell with the electrode is possible to be submerged in the water or treated with the with the drop sample that is to be analyzed, and this, as is a general working principle of the common electrochemical sensors that are widely used. For now, we are mostly concentrating, because PFAS are a wide and broad class of compounds, on PFOA, perfluorooctanoic acid, which is one of the most common PFAS compounds. In most of the countries and areas, it is now phased out of production and not used anymore, but it's still in large amounts registered across Europe in water, in soil, and in living organisms. The targets for applications are primarily as estimated environmental protection or monitoring authorities. On national level, this means ministries. On regional and local, this should be environmental protection and monitoring agencies. Also, possibly public health authorities like public health institutes that monitor the harmful effects of pollution on health. Also, agricultural or veterinary authorities dealing with animal health and with spreading of PFAS pollution through mostly internal waterways, also marine, and communal public enterprises, particularly the water supply companies or public institutions, or any other institution or organization which has in its domain quality of water and the spreading of and management of pollution. The sampling is possible not only on marine and the sea waters, as is the case in piloting in IMERMAID, but also in fresh waters and internal land water bodies and water flows. The preliminary actions and prerequisites should not be too demanding. So the beneficiary, of course, which is kind of implicit, should ensure physical access on site and installation and access capabilities to the water body or installation positioned on land, wherever is the location or area susceptible to sampling and to PFAS pollution. And of course, a mandatory prerequisite is the secure data connectivity. Otherwise, it would not be possible to relay the measurements onto the central system and the dashboard application, which we are providing to the beneficiary for overall consolidated analysis and monitoring of the results. The expected outcome is, of course, primarily the additional showcasing and the proof of feasibility of MERMAID solutions in local or regional or national applicability or scale up. And it would also be a proof of the electrochemical solutions, among others, that are employed in the project. Then this should pave the way for a wider adoption of monitoring of PFAS, which is happening currently in many areas, not only in Europe, and generally PFAS prevention, monitoring, and management is spreading globally. And as it is a large class of compounds and the effects are multivariate and heterogeneous, there is still a lot of exploration and many things are still not understood about how exactly PFAS is managed and how can it produce harmful effects, and what is the most viable and most effective solution for preventing or remediating it. So the idea is that the open call project or projects that are involved or choose to be involved with this have also high potential for contributing to the discovery of new insights and to increasing the body of knowledge on PFAS pollution. What we are offering, of course, aside from the mentoring and the technical support that is provided by all the technical partners from the IMERMAID project in this open call, we can also offer a limited number of prototype devices that will be available from January next year for deployment on the beneficiary site and using the device as described in the previous slides. Of course, providing that because these prototypes are still one of a kind and they have high value, that they are properly covered in terms of all damage and insurance in the agreement that will be made with the winning beneficiary. So looking forward to applications in PFAS field and scaling up IMERMAID solutions in this specific area. Thank you.
My name is Liza Volkova, and I am from the Department of Mathematical Modeling and Data Analysis of National Technical University of Ukraine. I will be talking about one of the solutions for chemical pollution monitoring and prevention. The solution name is Oil Spills Monitoring Model based on Sentinel-1 satellite data. Our solution is a deep learning linked net model, which is a type of computer program that is designed to learn and make decisions from large amounts of data. It's inspired by how the human brain works. The model is capable of identifying oil spills in oceans and seas. It can detect these spills by analyzing satellite images and pinpointing the affected areas. This makes it a valuable tool for monitoring marine environments and ensuring the health of coastal waters. LinkNet is a type of deep learning model used for tasks like identifying specific areas in images. It was chosen for our project because it connects different parts of the model, which helps keep detailed information even after simplifying the images. We used a method called transfer learning, where we took a LinkNet model that had already learned from a large set of general images, ImageNet, and fine-tuned it with data specific to our task. Our training data came from Sentinel-1 satellite images taken from 2018 to 2023. We tested the model with the new data from 2021 in the Atlantic Ocean and 2022 in the Mediterranean Sea. The results show that the model can effectively identify oil spills. The LinkNet deep learning model is designed to detect oil spills in marine environments using satellite images. When Sentinel-1 satellite data is available, the model can quickly analyze the data and provide detailed maps for oil spill locations in a GeoTIFF format. For example, it can process a 20 megapixel image in about 1 minute, making it efficient for real-time monitoring. Additionally, the solution leverages cloud computing to handle large amounts of data, ensuring that it can be scaled up as needed. This cloud-based approach allows for efficient data processing and storage, making it accessible for various stakeholders involved in environmental protection and disaster response. The solution would be ideally suited for environmental agencies, coastal authorities, research institutions, and environmental consultancies involved in monitoring and managing marine oil spills. These organizations can use the model to enhance their surveillance capabilities, improve response times, and make data-driven decisions for the preservation of marine environments. About suggestions for preliminary actions conducted by the beneficiary, the raster map on demand, GeoTIFF format with the results of oil spills identification for further analysis and usage can be provided. Also, in the case of further model usage, AI specialists and data analysis will be required. The model's ability to accurately identify oil spills helps to respond promptly to potential disasters. By providing up-to-date information, local authorities can take immediate action to minimize environmental damage and protect marine ecosystems. The model's result also assists in planning and executing cleanup operations, as well as assessing the impact of spills on coastal communities. Talking about access during the IMERMAID Technical Assistance Program, we can provide the oil spill detection model and its weights, code to run the model, description of the requirements for the model usage, and support and brief consulting for model usage and deployment. Thank you for your attention.
Our next group of IMERMAID available solutions to applicants under our Open Call 1 are chemical pollution remediation solutions. The first one is microfluidic water remediation system presented by Abhilash Venkateshaya from Eden Tech.
Thank you, Eddie. Hello, everyone. I'm just going to briefly give you some information on the microfluidic system. Microfluidic wastewater remediation system combines the advantages of two fields. That is, one is the advanced oxidation process, and the other one is the reaction on a chip. So in this system, we take advantage from both of these realms. For example, in the advanced oxidation processes, we know it's safe and it's a safe technology wherein it utilizes the light source and degrades a vast range of micropollutants, and it is a non-selective in nature as well. While in case of microfluidics, we have advantages because the flow is constrained within the microchannels, so that gives rise to what we call process intensification, wherein because of the large surface to volume ratio, the micropollutants are degraded quite efficiently, and also we have a lot of control on the flow as well. So some of the main features of the technology is the microfluidic system consists of the microfluidic networks imprinted on typical CD-shaped disk. The volume of water treated will be corresponding to the number of disks that are stacked. And it can be adapted to the application from domestic to the industrial applications, depending on the number of CDs that are stacked on top of each other. And as you can see from the video, the system is quite compact and works with an energy efficiency and is customizable as well. It's an innovative technology, but it's a tertiary system designed to treat the micropollutants. Its compact design makes it easier to integrate into the existing infrastructure of the wastewater treatment without significant modifications. And as I mentioned earlier, it is customizable to meet diverse application from domestic to industrial. And it is energy efficient as well. So it operates at low pressure. So the only requirement is from the light source that we'll be using, and makes it an environmentally friendly option as well. So some of the suggestions that we have for the beneficiaries for the open call to some of the works that could be are like identifying specific micropollutants that are prevalent in the region, conducting feasibility studies, being techno-economical analysis, operational feasibility analysis, and so on. And also providing specific technical requirements, which could include some of the parameters and the integrational needs, and also the capacity, that is the volume of the water that needs to be treated, and so on. And also create like a roadmap and strategies to replicate the system in the associated region. The expected outcomes include the detailed analysis of the micropollutants that are present in the region and corresponding to probably some of the activities in the region, be it tourism, agriculture, and so on. In-depth analysis of the viability of the system, the sustainability aspect, the financial, the techno-economical, and also comprehensive documentation for the microfluidic system requirements for the integration and the replication in the associated region, and the roadmap for the complete application of the system as well. So during the project, we can provide certain assistance and mentoring, which include the access to the experts in the relevant fields and mentoring throughout the project, supporting the feasibility assessments by providing data and inputs, access to the use cases during demonstration phases to collect information, obtain feedbacks, and so on. And also regular meetings and assessment to track the project progress as well. Thank you.
Next from our chemical pollution remediation solutions is the HiNaPEF post-discharge plasma presented by Simone Barletta from IRIS.
Okay, so our solution utilizes high voltage discharges underwater to mineralize organic pollutants and contaminants of emerging concern at various ranges of concentration. This solution is also capable of inactivating bacteria and microorganisms and prevent algae formation. This treatment working at low temperature is also suitable to treat edible liquids and ensuring their preservation of the organoleptic properties. The solution can deliver through its high voltage generator very narrow pulses of high current, high electric current. And in turns, these electric pulses generate reactive oxygen species and radicals. and also mechanical shock waves, and also intense wideband light pulses, which includes UVC light. The main feature of this technology is that it doesn't need any additional compound to perform its action, its treatment. The application and the practical use of this solution are, for example, the PFAS degradation directly in solution. Here we show, for example, the removal of some PFAS from wastewater. Other potential application includes industrial wastewater treatment facilities such as textile industries, pharmaceuticals, chemicals, and food processing plants. The wastewater that are more suited for our treatment are those that contains organic compounds that are difficult to break down using conventional method. So it might be of interest of local administration and wastewater treatment plants with contaminants in the wastewater of emerging concern. So what we suggest to assess if this solution is suitable for you is the study, a feasibility study to assess the technical compatibility of the PDP system with your existing processes and infrastructure. This evaluation, this feasibility study should be based on chemical analysis which are due to assess the contaminants and their loading on the wastewater that you want to treat, and also evaluate other physicochemical parameters such total organic carbon, pH, and conductivity. The outcomes expected from the application of this solution are a study of the effective degradation of various organic pollutants and the eventual formation of secondary pollutants. The demonstration of the potential of the solution to be integrated into existing water treatment infrastructures for various sides of water treatment, promoting water reuse and circular economy principles. The feasibility and the replicability should be demonstrated in different regions and for different application to pave the way for a broader application of this solution. A production of comprehensive documentation and training to facilitate the implementation should also be drawn. And finally, this solution should be able to engage stakeholders, for example, local authorities, industries, and communities, resulting in enhanced awareness and education on sustainable water treatment practices. The support and the assistance that we can give during the activities of the open call are a full access to the application of the HiNaPEF PDP technology, and also we are going to help on the feasibility studies and with some mentorship for the application of the solution. Thank you. I've concluded.
Our next chemical pollution remediation solution is the 4D Scavenger for removal and recovery of heavy metals, presented by Elmeri Lahtinen from WeFiner.
All right, thank you. So I will be telling you today briefly about our new 4D Scavenger technology. And as heard in the introduction, it is basically a new technology for removal and recovery of dissolved heavy metals from industrial wastewater. So basically, you can think of it like a filter unit, but for dissolved components in your wastewaters. And while we are also recovering these heavy metals from the wastewaters, we are also recovering them at the same time. So for some applications, even simultaneous removal and recovery are possible. But let's look a bit more closely into what 4D Scavenger actually does. So in this image, let's imagine that the feed water is any type of industrial wastewater that has an excessive amount of toxic heavy metals, let's say copper, nickel, zinc, cadmium, anything along those lines. So what we do is we actually customize the 4D Scavenger to remove those specific heavy metals from the industrial wastewater. So how it works after the 4D Scavenger has been customized is that we basically just pump the feed water through it and clean water comes out. Now these heavy metals don't magically disappear anywhere, so they're loaded into the 4D Scavenger itself. And once the 4D Scavenger is full, we simply wash them out with typical industry chemicals. Depending on the process, they can be salt, sulfuric acid, sodium hydroxide, basic chemicals along those lines. And after that, the 4D Scavenger is once again ready for reuse. So where this is applied, like I said, industrial wastewaters ranging anywhere from mining to chemical industry, landfills. Obviously, in this project, we are mainly focusing on this kind of effluent streams from processes, and I think it's a good example here that is presented. It's actually one of the use cases from this project itself. It's actually one of the internal pilots that we are going to be testing for this Scavenger for removing any remaining hazardous heavy metal residues from wastewater treatment plant effluents. So basic idea is that we are able to remove those pollutants before they are basically getting into the sea. And basically what's the suggestion here is that if the applicant or the beneficiary is able to share basically basic water analysis data regarding heavy metal concentrations, suspended solids, pH, this kind of very basic analysis of their wastewater, we can already have an initial technical feasibility checked for that wastewater, and then provide them with information if 4D Scavenger would be a suitable solution for removing those heavy metals from the said wastewater. And basically, what's the expected outcome of this? Is basically the analysis report if the 4D Scavenger would be feasible solution for the said wastewater treatment, and basically the roadmap on how to get forward. And first steps of this roadmap are also offered here for the applicants. So those are basically consultation if the 4D Scavenger would be a right solution, as well as some laboratory testing that is also available. Basically, this includes sending samples of the wastewater, us providing the testing and the 4D Scavengers that are required for those tests, and basically reporting the feasibility study results after those tests. And that's basically 4D Scavenger in a nutshell. Thank you.
Our final chemical pollution remediation solution is a non-destructive characterization and treatment system of old end-of-life reverse osmosis modules. This solution is going to be presented by Professor Ahmed Hanachi from ENIC.
Thank you very much, dear Ali, for this kind introduction. Welcome, dear attendees, and thank you for your interest. Here we are addressing a worldwide critical issue of the piling of end-of-life membrane modules that should be wisely managed within sustainability and circularity point of views. Now, membranes are used everywhere. Basically, they're used in desalination. You know, we have a big water shortage, and we need to harvest water out of seawater and non-conventional water. That is why we are relying mainly on reverse osmosis. Eventually, membranes get fouled and lose their performances and then end up needing to be replaced. So they should be wisely managed. And most of those who practice these membrane separation process know that pre-treatment and flow hydrodynamics within modules is critical. And the idea is to address the hydrodynamic pattern within these membrane modules using resistance time distribution. The idea is to inject a tracer and analyze the literature at the exit and extract a bunch of relevant information on the flow characterization within the modules. So along with the hydrodynamic characterization, also we need to check the separation performances of the membrane modules. And this is done within the same pilot unit, which is cheap and easy technique, and also with which we could combine treatment and cleaning and other processes for the modules. So we will assess fouling and cleaning extent in these end-of-life membranes and unfold also best cleaning and treatment protocols and the best operating condition. So, for example, reverse osmosis membranes could be converted into loose dense nanofiltration modules, or loose nanofiltration, or even ultrafiltration modules. So also we could define the best design and operating condition when we use these recycled or regenerated membranes. So the pilot will, of course, we are expecting to use the pilot mainly for industrial application, for industrial modules, 8-inch modules, but also we could accommodate different sizes, like the one we are going to use for our open case 2 in Opalia, where the used membrane, you see 2.5-inch diameter membranes, is used to pre-treat or pre-filtrate water that will enter the intensified advanced oxidation process already presented by our colleague Abhilash from EdenTech. So now, if you would be interested in applying such techniques, probably you need first to identify your existing target pollution remediation objectives to stay within the scope of the activities eligible for funding. Most probably you will somehow need a membrane process, either within your treatment process or even using these end-of-life membranes outside of your process. So probably also you need to gather as much as data as you can on operating these membranes, either new ones or old ones. You need also to conduct investigation on life expectancy and the prospects of using these end-of-life membranes. And also you could request support for preliminary characterization and treatment operation on fouling membranes and assessing the benefits of our pilot. So membranes are omnipresent in all pollutants handling processes. So you've got a big chance to be within the scope of the IMERMAID card. Even these processes are cost effective and modular. So you could be also within the budget allowed for these projects. So the idea is also we will obtain results not only at a lab scale or pilot scale, but also at an industrial scale. And the replication would be much easier. So we will allow tackling, replicating, extending, and developing multi-objective, innovative environmental solutions within the IMERMAID scope, handle pollutants, but also harvest water at the same time and recycle these end-of-life membranes. So we are available for joint assessment of your activities and the potential for relevant opportunities within the IMERMAID open call. We could also provide technical advice and support to help respecting open call objectives. We can offer also the IMERMAID consortium expertise for all preliminary assessment, as well operational systems, site visits, online visits, and demonstration activities. System and solution implementation mentorship, provide support and assistance for experimental investigations and data analysis, and open also to extend to perpetuate the results beyond the project period, which is 9 months, very short period. And thank you very much for.
A final category of available IMERMAID solutions for open call applicants are the public acceptance and community engagement solutions. Under this category, we're going to present the blockchain-based traceability compliance labeling, or TCL. The solution will be presented by Vladimir Urushevich from Zentrix Lab.
Yes, thank you. This class of solutions is for public acceptance and community engagement, and also striving towards, as the title says, compliance and practically regulatory compliance that is supposed to be increased overall together with the traceability, and using the distributed ledger technologies like blockchain, which is relatively common and getting more common now in pollution and waste management. Otherwise, these solutions for traceability and labeling and compliance are very common in supply chain management and generally in traceability in the industries which are already present partly and targeted in IMERMAID, particularly agri-food production, pharmaceutical and textile, which happen to be also the main classes of upstream polluters of the marine environments and the water environments. So the idea is that the beneficiaries, particularly the regulatory and governmental ones, or the ones generally concerned about the state of the environment and the pollution, will secure integrity of the data supplied or measured from the third parties involved in the waterways and the measurements themselves, of course, in field. And these data can be then exposed at fine grain, immutably recorded, and practically have a tamper-proof set of transactions that can serve for traceability and then later for labeling and compliance schemes, which would endorse the good practices and the good behaviors in terms of preventing and eliminating pollution. Technically, it is a sort of common and standard distributed ledger technology. It can be blockchain, which is quite common, but we can also support, like visible on the picture, DLTs based on directed acyclic graphs, which have their own advantages. They are based on energy efficient, low cost transactions, proof of stake algorithms, and ensuring scalability and performance through the use of production grade public infrastructures for distributed ledger. And generally, there is the data collection interfacing a set of APIs, which is connected or can be connected to the sensor technologies and generally monitoring or even remediation technologies like have been presented by now by the other IMERMAID solutions. Then the cloud infrastructure persisting the data into the blockchain layer, and the user interface dashboard that provides basic visualization of the data and that we offer linked to a public ledger and showcasing the data in human readable format. Of course, as in the example given here, the prover can usually is a company or an industry related partner, like we mentioned, and the verifier who actually drives the compliance and initiates the perpetual compliance and verifiability infrastructure is mostly the governmental or monitoring or regulatory organization or institution. The technology can be integrated, as mentioned, and is probably most convenient and most flexible through the APIs, which are exposed as classic web-based RESTful service APIs. And the main application, of course, is not only integrating the data and collecting the data acquired from sensors, but also supporting manual field measurements, so inspection services, all kinds of field control, and taking samples in the fields or sampling from, let's say, flowing waterways that can be immutably stored and traced and checked for integrity in a user-friendly manner. And of course, this can also be NGOs or even a governmental-based solution institutions that are mostly dealing with the public awareness and monitoring and public health as well. Preliminary actions are relatively straightforward, meaning stable and secure internet or intranet connection in the field necessary for acquisition of the data, and for proper and full integration and application using API endpoints, general ability on the, let's say, ICT sector or service or applicative support to do the basic setup and integration, for which, of course, we will all in the open call for provide technical and mentoring support. But this general ability and the staff on the beneficiary side would be very much appreciated and useful. The point, of course, and the goal is like the others, so successful further demonstration, scale up and showcasing of the feasibility of this type of solutions developed in IMERMAID. And of course, they contribute to the overall increasing of the compliance level in the general area of pollution monitoring, tracking, prevention, and elimination, particularly and conveniently driven by the monitoring or regulatory organizations and the beneficiaries. And of course, the labeling and certification schemes can be quite flexible and probably tailored by the beneficiaries themselves. So this is a basic technology infrastructure and ledger for paving the way towards implementation or say your own tailored labeling or certification schemes. So what we offer is the API integration that is flexible enough to include new sensor types through metadata definition, aside from, of course, already integrating and having a preset in the definitions and the configuration, the data and the sensory data sources that we already have covered in IMERMAID use cases and the demonstration work by now. And the platform will be fully operational and available from September this year. Thank you.
As you know, a core part of the IMERMAID project is the testing and validating of the developed solutions in 5 internal pilots. Today, we're going to showcase the IMERMAID use case methodology based on which our pilots have been developed. This methodology should serve you also in developing your own use cases with which you're going to be applying to IMERMAID Open Call 1. More information for the IMERMAID use case methodology can be found in Annex 1.1 technical description, available on the project website and part of the official documentation of our Open Call opportunity. This final section today is going to be presented by Eleni Christoforou from CMMI.
Thank you, Ellie, for the introduction. Hello, everyone, from me as well. So we're going to look into the IMERMAID use cases and the methodologies we use to establish them. So basically, IMERMAID has 5 different use cases, which they can be thought of as pilots. We have basically the general idea is to deploy and demonstrate the developed solutions, the solutions that you've seen earlier in the presentation, and to use a low-cost and energy-efficient demonstrators across different domains, use cases, regions, and different areas around the Mediterranean. As you can see from the map, we have the 5 use cases. Use case number 1 is at a wastewater treatment plant operated by Socamex. Use case number 2 is at the pharmaceutical industry operated by Opalia. Use case number 3 is at the wastewater treatment plant, again, operated by SMAT. Use case number 4 is at the marine environment operated by CMI, where we're looking at monitoring solutions. And use case number 5, we have at the leachate treatment plants. Again, you can see geographically placed there all around the Mediterranean, as we have Spain, Italy, Tunisia, Greece, and Cyprus. I would like you to notice a difference between this, where we have 4 use cases that are looking at the terrestrial sources, while just 1 use case looking at the sea. The big difference is that the terrestrial sources will basically end up at the sea, but it's very good to catch the pollutants before they reach the sea, while we have the 1 monitoring use case where we're looking at what ends up in the sea, but the concentrations, of course, will be much lower because of the dispersal in the marine environment. So going further into this, we're going to look at the aims and the solutions. As I mentioned earlier, we have both monitoring and remediation. So that would be the aim of your pilot, of the project that you're looking to do. What is, if you're going to be looking into monitoring the pollutants or remediating, or both. So in use case 1, we can see that it's about agricultural wastewater, and they're looking to both monitor and remediate pesticide, herbicides, fertilizers, and other chemicals. And this monitoring methodology is established by HCMR, while the remediation is established by IRIS, which is the discharge plasma water remediation system that you saw earlier. While for the monitoring, they will be looking in the bioaccumulation and biomagnification of the contaminants of emerging concern in the Mediterranean food web. Going to use case number 2, again, we have both monitoring and remediation. So monitoring will be by the use of the electrochemical sensor box, looking into the organic pharmaceutical pollutants like diclofenac, ibuprofen, and ketoprofen, while the remediation solution will be provided by the microfluid water treatment system. Again, I'm not going into much detail on the solutions, as you've heard a lot about it from each technology developer, but here I'm just giving an overview of what the use cases are and what the idea is about. Going to use case number 3, we're looking at the wastewater treatment. And we're trying to remediate and monitor heavy metals like zinc, cadmium, and lead by the use of heavy metal sensor and the 4D Scavenger technology for the removal of heavy metals. Jumping into use case number 4, it's only a monitoring one, as again, we're looking into the marine environment where there will be many sensors deployed on a buoy at the coast of Cyprus, basically. And we're looking at heavy metal sensor to monitor heavy metals. We're looking at oil sensors to monitor different oils, which will be coupled with satellite activity to see if there are any oil spills that are detected both by the sensor and by satellite imagery. And then we have the electrochemical sensor box. We'll be looking into nitrites in the area. As I said, remediation, it would be a next step, as it will be difficult to remove things from the marine environment. However, there could be some solutions for oil spills. Last but not least, we have the use case number 5. We're looking at leachate from waste from terrestrial environments, and we're looking at organic and the inorganic pollutants and chemicals, which could be monitored by the electrochemical sensor box and remediated by reverse osmosis and microfluid systems. All this is nice because we're looking what we want to do and what the solution is. However, it's important to look into national and regional legislation, because that definitely has to be satisfied before we can take any action. But at the same time, it could help us look into the needs of our country. Of course, each country has different legislations. There are the European-wide ones, Mediterranean-wide ones, but we also need to look at the purpose and the specific aim of the use case. Some of the legislations and directives are the Water Framework Directive, that looks into ibuprofen and biophenol A concentrations and other limits for wastewater discharge. We have the Marine Strategy Framework Directive, which it's more general about the marine environment, which in my opinion, it should be taken into account in all use cases, as everything will end up in the sea in one way or another. And then we have the Urban Wastewater Treatment Directive, looking at the amisulfite and benzotriazole concentrations, the directive on the quality of water intended for human consumption, the directive of environmental quality standards in the field of water pollution, waste framework directive, and of course, other regional environmental authority licenses are required, and local licenses and permits. So this list is not extensive, but it's a good start to look into what's needed based on the pilot you're looking to take part in. Further on, we need to look into the requirements and the KPIs. Basically, the requirements, we're looking into functional and non-functional requirements. The functional is basically what needs to be taking place in order for the results to be accumulated. For example, we need to provide real-time measurements of the concentration of targeted micropollutants and molecules like ibuprofen. And it needs to provide information through user-friendly monitoring interface. If it's something it's not understandable by everyone, then it will be hard to deal with. And then we have the operation in certain conditions. Again, going to the marine environment scenario or use case, we need to make sure that the sensor developed or whatever technology we're using can be effective in high salinity environments due to the salt water. This could apply to freshwater environments as well. Maybe the pH is different, so it's good to think of what is needed for the technology to function. And then we're looking into the uninterrupted electrical supply. That could be a parameter that needs to be satisfied for the technology to work, and of course, reliable data communication. Looking at the non-functional and the KPIs, it's more about what the results will be. So we're looking at the detection of specific minimum concentrations. So if the sensor is not developed to catch the lowest concentration that we're looking, then it might not be what we're looking for. And then we're looking at a set percentage of reduction, which would be a KPI, and how much we're looking to reduce. Of course, that's applicable only for the remediation solutions. Monitoring, you cannot set a percentage for reduction. And then we need to set the response time and the refresh rate. For example, for seawater, 30 minutes are adequate, but for something that changes more frequently, we might want a lower refresh rate. Going on, we have other considerations to keep in mind, which is the time availability, and to create a timeline, the allocated budget, the personnel, the preparedness, and the expertise, of course, the disposal of any chemicals, the maintenance requirements, consumables, data processing, and the evaluation. With that said, we've seen our purpose, our aim, and the research behind it in terms of legislation and what we want to develop and do, but we need to be able to validate all this. During the timeline of this project, it might not, like a scenario might not occur, like a case might not occur where you can test the exact concentration or conditions that you're looking to. So to overcome this, it would be good to create scenarios where through these scenarios, we will basically create situations that are likely to happen for the technologies to be tested and validated. Example of this are like, we create a scenario where an increase in the concentration of ibuprofen is affected by the electrochemical sensors placed at wastewater treatment plant. And the validation process would be to test for the continuous measurement of the pollutant and to apply and test remediation technologies using before and after measurements. So basically, we're creating like a scenario, and then we're testing if our technologies are actually working under those conditions. Another scenario could be that a high concentration of heavy metals is detected within a short period of time that would have not been detected during periodic analysis. That was something done before the IMERMAID project technologies. And to validate it, we need to perform laboratory analysis to validate the measurements. So double check that everything works well and to test the continuous measurements of the pollutants. Lastly, another example, going back to the sea environment, is that an oil spill incident had occurred and high concentration of crude oil are detected. To validate this, we will check other sensors that are placed on the buoy, for example, the pH. If we see variation on that, then we also check the most recent satellite images to double check again that there is indeed an oil spill. And through the process, we ensure that there is action protocols in place. So if there is an actual oil spill, we know what to do, who's responsible, and how to act. Of course, each case can have multiple scenarios different. These are just examples to understand how we would validate the process. Last but not least, you also have it in one of the annexes of the document you have received. This is a checklist that we have used also for the IMERMAID use cases, where it helps basically to make sure that you have all this information, which would help in the organization of your pilot, of your use case. So first of all, we need to think of the objective, the location, the type of facility, the activity of the facility, the processes included, the target contaminants and parameters that could be monitored or remediated, or both, the impact to the target chemicals if they're remediated, the technology that can be installed and the validation process, the description, which is basically the scenarios that I explained earlier, the specific requirements that need to be in place, KPIs, which is the aims and goals, existing constraints, regulations and technical alignment, stakeholder identification, expected outcomes, and the timeline. Thank you for your attention.